Hello YouTube and welcome back. What you see here in the field is the beginning of a project that I'm actually very excited to get started on. My bench needs better lighting and I'm going to accomplish that with these. Now what these are is 6-watt LED cobs, and what cob stands for is chip on board, which means each single one of these bars here has 72 LEDs on it with a sort of a silicone covering with phosphor in it that determines the color of the LED. What I have here are 3 warm white and 3 cold white LED strips in the hope that once I've got them mounted up on the underside of the shelf here, they'll make this whole workstation glow with a nice even light, and there won't be all these sharp shadows that are being caused by the halogens that I currently am using. So what we're going to do today is explore the science of driving one of these a little bit, and then in a second video I'm actually going to construct the whole project using some other materials I've got here. I'm going to fuse it, and it's going to have a switch and some other fun stuff going on. But for today we're just going to discuss a little on the science of how to drive these. Now ideally, with large LED strips like this, you'll want to use a constant current LED driver, which is going to constantly adjust the amount of current going into the circuit based on a predetermined amount. So LEDs are a current-controlled device, and they will pull as much current as they possibly can right up until the point where they self-destruct. So you want to prevent them from doing that. So you can do that with these current-controlled chips. I haven't managed to order any yet because the ones that would be best suited for this purpose are only available from China, and I can't afford right now to order them. So instead, we're just going to do a simple voltage divider circuit to drive these LEDs. Not nearly as efficient, and you have to worry about some heat dissipation problems, but we're just going to run with that for the time being until I'm able to get the components for the more advanced circuit, and then we'll do a third video on setting up the LED lighting. So for now we're just going to talk about the science behind these chips, and rather than doing it with 6 chips, I'm just going to do it with this one. This is one of the ones that I was doing testing on, just in case I overdrove it or blew it up or made it catch fire or something like that. It was just one that I was going to sacrifice to the altar of science if necessary. So we're going to just quickly set up a voltage divider circuit here, and you're going to see a lot of these in this channel. And so we're going to have our plus 15 volts. That's what this power supply is here that we're going to use to drive the circuit. And it's going to come through a current limiting resistor there, and then through the LED package. I'm not going to draw all 72 LEDs because we'd be here for an hour and it wouldn't serve any particular purpose. So these cobs are rated at 500 milliamps each. So when we're wanting to drive one at 12 volts, we know we want 12 volts here, and we want 500 milliamps. But we've got 15 volts coming into that circuit. So we've got 3 volts extra that we need to dissipate across this resistor. So we know that that resistor needs 3 volts. We also know that we want to use that resistor to limit the current to 500 milliamps. So now that we know the voltage and the current, we can solve for what the value of that resistor needs to be. So our staple Ohm's law, voltage equals current times resistance. We'll slap that with a bit of algebra because we want to solve for resistance. So resistance equals volts over current. So I'm just going to grab my calculator here so that I can show you the math in process, and by calculator I mean my phone. So we've got our volts is 3 volts over 500 milliamps equals, and we're going to take 3 divided by 500 times 10 to the negative third, and we're going to get a value of 6 ohms. Now unfortunately, that's not actually a standard package for a resistor, at least for these power resistors, which I'm going to have to use, and we'll get more into that in a couple moments here. So I've actually got a 6.8 ohm resistor here. Well, that's for running it at full brightness. So that's going to actually be really quite intense. Now, the reason why I've got these huge resistors here is if we take 3 volts and multiply it by 500 milliamps, so that's 3 times 500 times 10 to the negative 3, we're going to be dissipating 1.5 watts across that resistor. Now your standard resistor, this little guy, that's a quarter watt. So 1.5 watts is, what is that? 6 times what this resistor can handle. So if we put 1.5 watts across this, it would start smoke and it would catch fire. Literally, these do actually catch fire. And if you put way too much current across them, they will actually explode. I may demonstrate that on one of my videos, but one of the channels I watch, Big Clive, he does it on a fairly regular basis just for fun, so I'll probably link one of his videos in the description below. So we've got a 6.8 ohm resistor here that's rated for 10 watts. So it's not going to get nearly as hot as a quarter watt resistor would, of course. And even if we went ahead and said, hey, we only need 1.5 watts, so let's go buy a 1.5 watt resistor, which they don't exist. You could buy a 2 watt resistor. But at its maximum current dissipation capability, a resistor is going to run at about 100 degrees Celsius, and we don't want that in our circuit. We want the resistor to stay fairly cool. So we're going to overrate the resistor by a fair deal in order to make sure that things don't overheat. Now, I'm pretty sure I'm not going to want to run all of these cobs at their full rating for 2 reasons. One, they'll be extremely bright, and I don't need all 6 of these bars to be running at full brightness. And 2, it will actually shorten the lifespan of the LEDs if we're running them through this standard, through this cheating with the voltage divider rather than constant current driver. So I'm thinking maybe I want to run it at perhaps 300 milliamps. Oops, that's 3 milliamps, 300 milliamps. So we'll do our math there again. 3 over 300 milliamps, 3 volts. And I already know the answer to that, but I'm going to show you guys just because. So we've got 3 divided by 300 times 10 to the negative third, and that calls for a 10 ohm resistor. I actually have a 10 ohm resistor right here as well, so we'll be able to test that brightness. I also previously did the math for this and grabbed an 8.2 ohm resistor that'll run it at about 400 milliamps, and a 15 ohm resistor which should run it at about 250 milliamps. So all of that boring, uninteresting math aside, let's actually start hooking up some power and show you what these actually will look like when they're illuminated. Now, I haven't yet modified this power supply for this project, so let's go ahead and make this work for our purposes. So I'm just going to use my diagonal cutters, and we're going to nip off the ends of those wires, and I've left my wire cutter somewhere else, so give me a moment and I will be right back. Alright, then I'm back after finding my wire strippers here. These are actually some very high quality wire strippers that came with my toolkit for school that I've been really enjoying owning. I wouldn't have bought these normally because these cost like 30 something odd dollars, but I'll be content to use them being as it came as part of my tuition. So these are neat because they've got the different ratings of different wires here. The one side for solid, the one side for stranded. And this power supply is nice because it says right here on the wire that it's 18 gauge wire. So we'll just slip that into the 18 gauge slot there and we'll nip it, and it automatically cuts through the insulation without cutting through the wire. And then we can just give that little bit of waste insulation a twist here, and it will twist that stranded wire up nice and tight so that I can then proceed to tin those wires. So I'm just going to give them a little dip in some flux. That's what it's called. I was going to say rosin, but that's not the correct term. Tin the tip of my soldering iron a little bit, and then we're just going to tin these up real quick. Just like so. Probably needs just a little bit more. There we go. So now that those are tinned, we can proceed to determine the polarity of it. Now, I know from the diagram on the power supply that the outer sleeve here is the negative terminal and the inner sleeve is the positive terminal, but I have no idea which wires that corresponds to. So we're just going to plug this in off camera here for a moment. There we go. Being very careful not to accidentally short those two wires together, although the power supply does have short protection on it. I'd have to unplug it and start over again. So we're just going to turn the multimeter on here. Now I'm going to gamble that the wire with the stripe is going to be the negative wire. So I'll put that on the black lead and then the other one on the red lead. And I'm going to get a very strange reading. Let's actually just do it this way. There we go. So that reads actually as negative 15.45 volts, which means that the positive wire on this is the one with the stripe. So we'll remember that that's the positive terminal, and that's important to remember because LEDs will only take current in one direction. Now, the next step here is to actually connect up the circuit. Now I'm going to do just a basic circuit here. We're going to clip that on like so. Clip that on like so. Oh, come on, get on there. There we go. We're going to run that into that hole in the proto board. And then we're going to grab my great big honkin' resistor here. This is the 6.8 ohm one, so this is going to be running this LED at 500 milliamps. So this is going to be rather extremely bright. Now how do I want to do this? So we're going to do that, and we're going to pick another row of the proto board here. I'll go into more detail on how these proto boards work in another video. Let's see. That's my negative terminal, and then it's coming through, and we'll put that through there. And I'm kind of hoping that I can just sort of cheat and get these into those holes, which I can't. Okay, so we're just gonna take the negative terminal and hold it to the negative wire there. This is only 12 volts, so I don't have to worry about electrocuting myself or anything. But this is what one of those cobs running at 500 milliamps is going to look like. that was anticlimactic. What did I do wrong? Let's see. Oh, hey. Remember what I was saying about the polarity of the LEDs? I bet if I got that correct, it would be much more interesting when I connect to power. So, this is the negative, so that's going to that terminal. And let there be light. So that's really very bright. I just looked directly at it, and now I've got 72 little bright spots in my eyes, and you guys probably can't see anything because it'll be washing the camera completely out. So let's go to the far end of the spectrum in the other direction, and we're going to grab this 15 ohm resistor. We'll try that one. So click that in there. And we'll do, come on, get on there. There we go. Okay. And rule of thumb is to always connect to the negative terminal first and then apply power. So we're going to apply power, and that's still actually very, very bright, but not quite as bright as the other one was. So I think I'm definitely going to be running these at less than 500 milliamps for a number of reasons, not the least of which is 6 of them running at full brightness will be incredibly bright. So just for fun, let's see what it's like with a 10 ohm resistor here. I wish there was a better way of comparing the brightnesses. So we'll just quickly throw that on there, and throw that on there, and where did my power go? So we'll do negative terminal here, positive terminal here, and even that is noticeably brighter than the previous. So we'll just have to experiment off camera a little bit once I decide which resistors I'm going to use for the full set, and we'll come back and build the whole circuit together. So thanks for watching. We'll see you soon in the next video when I build the entire circuit, and thanks for watching. Bye-bye.